question number one, as before, either you know it or you don't. And I know I gave you 4 again, so it's because we're getting into copolymers, so I wanted to talk about 4. And 1 because it's a complicated question, but a lot of people did pretty well on that one. Okay, so question 2. XRD of polymer crystals carries with it certain limitations. And so as we discussed, evaluation of crystallinity in polymers with XRD has its limits because they are not good scatterers. And so I wanted to try to hammer that home. First of all, described by plastics can never be 100% crystalline. And yet they have fold surfaces is the very basic component of it. It's not because they have entropy. Entropy doesn't keep them from being crystalline. It's the fact that fold surfaces exist, and they have to exist. And therefore, you always have amorphous content. There are other reasons for that, which you could discuss and gotten credit for, but that's the fundamental limitation. It makes it impossible for things to be 100% crystalline. And then question B, why is XRD a primary tool allowing determination of crystallite orientation? So what I meant by was oriented crystals. So when you strain those polymer films in class and it goes from being circles to arcs, that's giving you information on orientation. All right, and that's what I was looking for. I got some other answers, but that's what I was really looking for here. And then question C, unit cell parameters. I was just looking for A, B, and C and how they vary as a function of temperature. And so that was right out of the notes. Why is XRD a primary tool? Because it measures orientation based on how much the arcs have been broken up, or the circles have been broken up into arcs or into points, even. Yes?
Were you looking for something about strain for B and C?
Not so much strain, although strain is one of the reasons why the crystallites orient.
Oh, you just wrote it on my thing.
Strain?
Strain.
Oh, I'm not there yet. Oh, wait, I'm in there.
Yeah, I wrote B and C.
Yeah. Oh, yeah, so you wrote break and I meant strain. So it doesn't break, it strains. Okay. Limitations of the two-phase model, and so this reflects on the fact that the border between crystalline and amorphous is a fuzzy thing. And we have crystals that grow and gobble up the amorphous phase at room temperature, and then it's easy to pull things out of the crystal, and so there's this in-between component that as material, because we like black and white answers, but in polymers and especially interfaces, the answer is not so black and white, and so that's the limitation of the two-phase model. Most people had that one. And then part E, just looking at the data, you wanted you to identify the fact that we have the overall measurement, and then we have the amorphous halo, which is pretty important to know about in context of XRD. And then we have the actual crystalline peaks themselves that have been assigned after you subtract the amorphous halo out. All right, so just looking for that information. And then part F, just take this and turn it into a circular pattern. And most people were able to jump on that and do that pretty well. And then part G, if the isotactic polypropylene is extruded into a fiber at high speeds, and that speed is taken directly from paper in the area, so this is what they do, 4,250 meters per minute, which is flying, you'd expect that to cause orientation of the polymer, because you're straining it dramatically as it comes out of the extrusion die at 4,250 meters per minute. Okay, and so that's going to break up your circles into arcs or even points. All right, but mainly I was looking for degradation of what you had in F into something that reflected the fact that it's under an enormous amount of strain, thousands of percent. Okay, any questions about all that?
Can you repeat that? Part G?
Part G, so you have this enormous amount of strain. It's probably a 1,000% strain versus what came out of the die, that allows it to be extruded at 4,250 meters per minute. So that's a ton of strain. We talked about the pictures. We start the circle, 100% extension, 200% extension, 300% extension. It's even worse than that. All right, so you're talking about straining this matrix, causing those crystallites to orient because of the enormous amount of strain that's being applied to that material. And that's you get the orientation, and you get the dots or the arcs instead of circles.
All right.
Any other questions? All right. And question 3 I'll go over at the end. So what I've done is I've asked you as a homework assignment, as a basically redo this test question, because I felt like a lot of people weren't really getting it as far as crazing is concerned. And so what I want you to do is go through this, and you can do it collaboratively if you want to. Some of you have the right answers on your test. Those answers should still be right when you turn this in. All right. And what I've done in the assignment, which I don't have here, but if you look at what I sent out in parentheses at the end of each sentence, I have whatever it is, 46 words or less. All right. And so this is to confine your writing to be concise and precise in the answers. Now, you guys have looked at my keys. You know I write way more than you write when it comes to the answers to these tests, right? Because I'm trying to be very definitive and very precise and give you lots of information in the key, because I know you guys learn from looking at the keys. So don't write more than I do. You should have no reason to write as many words as I have. You should be able to write fewer words and answer these questions correctly. Okay, but be on point. And one of the key differences here, or the issues here, was that there's the initial stage of crazing, which, as I hammered you guys many times, is based on hydrostatic stress, and then there's growth, in which the crazes actually exist. Otherwise, why would we be talking about growth? All right, and so that forms a lot of the basis for this question, and make that distinction in your answers. I think that's everything. Any questions about that? So what I emailed you in a very scary way is going to give you the number of words that you should write fewer of in answering these questions. Say what?
We can work on it with people you said.
I can't hear you.
We can work on it with people you said.
Yeah, sure. All right. Any other questions?
So, when we do this assignment, is it going to give points back for the test, or?
Yeah, I'm going to add these points on your test scores.
Okay.
So the penalty is in not doing it. All right.
Penalty is in not doing it, especially since it's going to shift the average most likely.
It depends on how everyone does. If everyone gets the full points on this, then they'll all be shifted evenly.
All right. And how do we submit the answers to you?
You can email it to me as a Word or a PDF, or you can bring it in on Monday.
And did you mention the due date Monday?
Monday, yeah, it's in the email. I gave you plenty of time. I thought about making it due on Friday, but I thought, they probably have stuff going on, so I made it Monday. Yes?
How's the grading of this going to work? Is it just going to add on to our points of the test?
Yes, I'm just going to add it onto your test scores. I won't physically put it on your test, but in my spreadsheet it'll be added on.
For example, I'm missing 11 points here. Let's add 11 points to my total score.
You'll add, so
Assuming I don't mess up anywhere else, basically.
Well, you add 30 points to your score, or less than 30 points, depending on how you do in terms of the answers.
On this question, I missed 11 points, so I have the potential to make 11 points back.
No, I can't do it. I don't have your old tests in front of me, so I don't know how much to add back. So basically, you had this 30-point bonus that you can either accept or not accept. Yeah?
You delete whatever I got. Okay, I see what you're saying. Yes.
Okay. Any other questions about that? All right, we're good? Okay, see you guys on Friday. Feel free to ask me any questions. Question 4. The data below refers to observed aspects of crazes created in thin films of polystyrene at various temperatures. Based on your knowledge of the crazing process, A, explain why polystyrene fibril diameter increases with temperature. And so here I was looking for, first off, starting with an acknowledgement that active zones exist, and how active they are is a function of temperature, and how easily they can draw polymers into these fibrils as they grow. And so if you go to a higher temperature, the process of drawing in polymer chains into the fibrils becomes easier because of the fact that temperature is motion, temperature is vibration. And so it makes sense that the fibril diameter should increase because it can pull in more material more easily That makes sense? So it really starts with the active zone here. I was trying to dig into the crazing a little bit more in this question. Briefly sketch the relative internal structure of a fibril formed at 20 degrees centigrade versus one formed at 70 degrees centigrade. So first off, the one at 20 is smaller than the one at 70. Start with that basis. And then I was looking for some acknowledgement of the coils. Mostly I got just orientation, which was okay, I guess. But yeah, that's kind of what I was looking for. What I really wanted to see was the fact that there are coils inside these structures. And there are going to be more coils across the diameter of a 7 degree C fibril versus a 20 degree C fibril. And those coils are interlinked vertically along the axis. That's kind of what I was looking for, but I ended up accepting just starting with the right diameter and showing that there's some type of polymer structure inside those fibrils that hopefully looked oriented in your sketches. And most of the time it was. Any questions about that? All right, and then part C, if the degree of chain entanglement could be controlled as easily as temperature, provide a schematic plot of how you expect diameter could change versus entanglement. And so here I'm looking for the idea that you can tune your entanglement as much as you want. What happens and when does it happen? So first off, if entanglement is on the x-axis here, so entanglement instead, if I have an entanglement of 0, do I have a fibril? Oh, I don't. All right, so there should be nothing down here because it's impossible for an entanglement of 0 to cause a fibril to form. All right, and that was kind of the basis that starts the plot. And then after that, it gets kind of speculative. You know, my plot was just a straight line. It's always safest to assume linear until proven otherwise. But if you had parabolic, that was okay too, right? But mainly I was looking for that type of dependence. You couldn't start with a large fibril diameter at 0 degrees of entanglement. That doesn't make any sense. So once it gets to a certain amount of entanglement, then the fibrils can form. And then beyond that, as entanglement increases, then the diameter also increases because you're pulling in more from the active zone and you're making that fibril a larger diameter, better able to withstand all the tensile forces that are acting on it. Any questions about that? Okay. Basically number 3. And part 5, question 5. So yeah, this is data taken directly from a paper. In this area, the injection stretch blow molding process is used to create all the PET bottles with which we are all familiar. So we use these day in and day out. Many elements of ISBM need to interact appropriately to achieve successful processing. Orientation, temperature, too much coffee, and stretch ratio are 2 of these variables. Orient temperature is the temperature at which the PET is deformed during which the polymer chains align in achieving a specific ratio or stretch ratio. Draw ratio is what we use in class. As you know, mechanical and barrier properties of PET are much improved by orientation. Table 5 gives you some data about diffusion. Give 2 reasons why the polymer orientation is important in the formation of PET bottles. I kind of told you that in the abstract. You have the fact that you need orientation to get certain mechanical properties. And you also need orientation to achieve certain barrier properties. So even if it's amorphous, which it could be, the paper itself talks about the breakup of crystals during this process. But anyway, you have amorphous polymer that if aligned acts as a barrier to orientation because those polymer chains are aligned. They can't move around much. Their entropy is much reduced, so they make a better barrier for orientation because the hallmark of diffusion is chains getting out of the way. And if they're aligned with fewer orientations, they cannot get out of the way as easily. It doesn't go to 0, all right, but it does decrease it. And there's at least there's another reason that some of you gave, which was also fine. How does temperature control the orientation process? So again, this is all about temperature is vibration, all right? And if we increase the temperature, it's easier to make those chains move and draw into oriented structures. All right, so I'm trying to hammer home the idea that temperature is motion. It's not temperature. increased crystallinity can be used to improve PET's barrier properties. So the question is, why does it improve the barrier properties? And it certainly does. The fact that we have much less space in a polymer crystal, the chains are tightly packed in that crystal, and it's even worse than just flat-out orientation. They can't move at all, because to move, they'd have to come out of the crystal. They'd have to melt. All right, so that makes it a very effective barrier. Again, not a permanent, impermeable to everything barrier, but it does increase the barrier properties of PET. Again, because of the fact that diffusion is chains moving out of the way. Any questions about that? And then examine table 5 and briefly explain why CO2 diffuses so much more readily than nitrogen or oxygen, both of which are smaller than CO2. And so what I was looking for here was the fact that like dissolves like, the primary rule that makes the most sense. Some of you could explain why PET likes CO2, because it's got carbonyls in it, and those are very similar to the carbon-oxygen double bonds of CO2. All right, and that was really what I was looking for. It's just like dissolves like, and acknowledgement of the fact that diffusion is permeation, and if the polymer can't load up with the CO2, it's not going to let it diffuse out either. All right. So the fact that it likes it means that it absorbs a lot of it, and then it can diffuse through relatively rapidly because there's so much of it running down the diffusion gradient and getting out of the PET. It doesn't like nitrogen and oxygen as much, even though they're smaller, so it doesn't load up with oxygen and nitrogen and allow for their diffusion as readily as it does CO2. Any questions about that? All right. E, why does hydrogen diffuse more readily? Because it's so darn small. All right. I gave you the example of the space plane and how it's just like it's like these 3D metal lattices are nothing for hydrogen to diffuse. Right? There's no barrier at all there because they're so tiny compared to those structures. And in this context, it's for the same reasons. And then part F, diffusion coefficient in PET is concentration dependent and increases the permeation of CO2 increases. It had to do with free volume. More CO2, more stuff between the chains, increasing the free volume catalyzes this nonlinear variation of diffusion coefficient that we talked about in class. All right, so that was based on the fact that polymers are not inorganics, which cannot saturate and change the lattice. You'd have to basically melt the metal or melt the ceramic to do the same thing that happens in polymers at room temperature. Any questions about all that? Yeah?
Can you explain the temperature stuff?
Part D?
B.
B. Oh, yeah. So the polymer chains and their ability to move and respond to stress are controlled by their temperature. And if it's 0 degrees Kelvin, they're not moving. All right. Higher temperatures they can move, and in this context, we're in the melt state. And so the higher temperature of the melt, the more easily they're oriented and aligned. And so it's a drawing process.
It would become less random, I guess.
Say what?
It would become less random at higher temperatures. More oriented.
More oriented, yeah. If the higher temperature melt is used.
Okay.
All right. Any other questions? Alignment. All right, and then last but not least, PET recycling. Targets the use of so-called chain extenders, which you saw already in one of the old tests, to combine reduced molecular weight polymer chains. An example of this process using this compound called PMDA is shown below. And again, the idea is there should be nothing scary about this. You have two pieces of PET that are reacting with this PMDA, which looks like a scary organic molecule, but it's just a connector. All right, it's just pulling things together. There's nothing that unusual about it. The difference from what we would normally be looking for is the fact that, and this gets into some of the things we're talking about now in class, it has 4 bonds to it, not just 2. So it's not creating a linear network, it's creating a thermoset or cross-link network where there was none before. All right, and so rather than just connecting 2 chains together and forming a knitted structure, it's connecting 4 chains together. And everything that comes after that is caused by that difference. And so this does a great job of connecting these pieces together, but it's doing more than just forming or reforming the linear chain that existed initially. And so what specific problem is this attempting to overcome? Hydrolysis, all right? Talked about that quite a bit. So water reacting with PET at high temperatures scissions the chains. It doesn't start at the ends, by the way. Some people talked about starting at the end. It'll start anywhere it can react with PET. It doesn't need to start at the end of the chain. Wherever the water is closest to those particular susceptible bonds, it'll react with them. It doesn't look for the end only. Okay, so part B, assuming the reaction goes to completion as shown, what effects on viscosity might these extenders have? And of course, you're causing cross-links in these structures. You're moving it toward the thermoset in terms of its character. The viscosity is going to shoot way up. All right, there's a limit to this, how much of this PMDA you can put into it and still be able to move it through a mold or pull on it at high temperatures. Even though it's a polymer, if it's a thermoset, it's cross-linked enough, it's not deforming, even at high temperatures. You can take it up to the point where it catches on fire, and it still won't deform if it's heavily cross-linked enough. All right, and so this issue of viscosity, and a lot of you caught this, is really important in terms of manufacturing because you have to make 1 million of them every week or every day, or when it comes to blow molding, it's probably 1 million every hour as far as that's concerned. But this process of extending it, pulling on it, requires that it be a certain viscosity. Any questions about that? And then part C, what effects might these extenders have on PET crystallization? I think most people got this. Obviously, it's going to, first off, it's not going to fit into any kind of PET lattice that might exist inside the wall of these bottles. Right? So it's going to damage the crystallinity that way, if you want to think of it that way. And also the fact that you've got this cross-link structure is going to combine a lot of chains into one spot and make it hard for them to move around. And if the chains can't move around really well, they're not going to be able to move into a crystal really well either. All right, so this type of structure with the thermoset-like bonding it introduces is going to have pretty large effects on crystallinity in these structures, even though there may not be that much of it. Okay, any questions about all that? All right, so yeah, okay. So let's go to the